Here's another example of calculating these atomic masses, or we call them weighted average masses. Now here it says atomic mass estimation, which we could estimate with easy numbers, but you can also have a calculator handy for these types of calculations. So we are given element X that has two naturally occurring isotopes. One isotope has a mass of 10 AMU and a relative abundance of 20%. The isotope of 11 AMU has a relative abundance of 80%. What is the atomic mass of element X? And when they say atomic mass, that means like the weighted average mass. Average. Whoa, I could do better than that. Average mass. So it's calculated. It takes into consideration the different masses that exist for that particular isotope and their percent abundance in nature. All right, so they've summarized the information in this little tables. We've got the knowns. We know the mass of each individual isotope, and we know the abundance of each. We are trying to find then the overall atomic mass as it would appear on the periodic table. So remember that the periodic table lists these masses as weighted average. Here's the periodic table that's at the very end of your textbook, and really there's so much junk in these boxes, but like when you see this mass number, it's up in the top corner. So like for neon, 20.180. There is no one isotope with a mass of exactly 20.180 AMUs. But this mass takes into consideration the different isotopes that exist and their abundance in nature. These are the average masses that appear on the periodic table. All right, so here's what I would do. I take the mass and I multiply by the percent abundance, but we use it as a decimal. So if it's 20% abundant, I'm going to plug it in my calculator if I have to as 0.2. So I take the mass of 10, plug it in my calculator. 10 times 0.2 is a whopping 2.0. And then I do the same thing with the other isotope. The mass was 11 AMUs. It's 80% abundance. That gives me 8.8. And that's kind of like the fraction of mass then coming from each isotope. Finally then, I add. We add the mass contributed by each individual isotope, and then 10.8 is what would appear on my periodic table. Now what they could do then, as like an extension question, they could say something like element X is blank. Like if this were real data for real elements, they could say, hey, like what is the identity of element X? It's this mystery element. Well, then I'm going to go to my periodic table and say, which element has a mass really close to 10.8 AMUs? And so the mass numbers do increase. They don't increase always by the same amount like atomic numbers do. But I'm kind of just looking at these little numbers in the upper right-hand corner. And again, this is on, oh gosh, it's like the page way at the end of your textbook. Like if you flip to the very back page, I forget what the number is. It's like something 50. Okay, so I'm looking at these little numbers in the upper right-hand corner. Beryllium is like 9.0122. Aha! How about boron? Look at that, 10.81. Not bad, right? That's pretty close. So I would estimate then that this element X is boron. So if we were given legit numbers, we could identify the element, the identity of the element, by looking at its overall weighted average atomic mass. Now at the end, it does say to evaluate your results. Does this number make sense? And so sometimes I think people like get too reliant on their calculators and I gotta plug everything in. They plug everything in their calculator and then they just circle their answer and they don't take a second to say, wait a second, that doesn't make sense. Now, number one, obviously, if the two isotopes are mass 10 and 11 and you plug something in your calculator wrong and you get a mass of like 13 AMUs, that can't possibly be correct, right? Sad face. That's not correct. I mean, the answer's got to be somewhere between your highest mass and your lowest mass of individual isotopes. It's got to be somewhere in between 10 and 11. It can't be 13. That wouldn't make sense. Okay, then the other thing that we look at is if I check the percent abundance, and this one is 80% abundant in reference to isotope mass 11. So then my weighted average should be somewhere in between 10 and 11, but much closer to 11. 80% of the atoms are mass 11. So yeah, then I look at my answer. Yeah, 10.8, that seems reasonable. If I would have plugged something in wrong and gotten like 10.2, that wouldn't make sense. Like, oh, wait a second, maybe I flip-flopped something. Oh yeah, it was supposed to be 80% for isotope 11. Whoops, I got that backwards, or something like that. That, yeah, it's got to be between 10 and 11, but closer to the more abundant isotope. Aha. Okay, so question 18 then said to use the information in this table to estimate. Interesting. Estimate the atomic masses for carbon and bromine and record your answers in the table. Okay, so let's look at hydrogen, helium, and nitrogen and see what we're supposed to do here, right? So for example, hydrogen exists as 3 isotopes in nature. There's hydrogen mass 1, mass 2, and mass 3. And again, when we see these symbols, like, you know, I'll do hydrogen 2. So it's got 2, 1, and then the H. The bigger number is the mass, and the smaller number is the atomic number. Atomic number. Okay, so like when I look at these 3 symbols for hydrogen, all of them have the little atomic number of 1. Well, yeah, because that identifies the element. 1 proton. All atoms of hydrogen have 1 proton. What can change is the mass, depending on how many neutrons. So like hydrogen 1,1, this guy right here, there. Hydrogen 1,1 is the simplest atom on the periodic table. So its mass is 1, and it has 1 proton. The atomic number is 1. All it is a proton in the nucleus and no neutrons. So simple nucleus, just a proton, and because it has to be a neutral atom, it's just 1 proton and 1 electron. That's it. Then when I move to hydrogen mass 2, the nucleus has a mass of 2. Well, it's 1 proton and 1 neutron, but still 1 electron. And then hydrogen 3 has a mass of 3, so there's actually 2 neutrons and 1 proton, and still 1 electron. Now look at these abundances in nature. So it's like 99.9, almost 9% abundant in reference to isotope mass 1. 99.9% of all hydrogen atoms are mass 1. Oh, look at the fraction of atoms that are mass 2 and 3. I mean, this is a percentage. So like this is saying 99.985%. 0.015% of the isotopes are mass 2, and the amount of hydrogen 3 on the face of this earth is negligible, so tiny. Okay, so then they give me the individual masses, and of course it's like really close to 1, 2, and 3. And then as an estimate, so here, when they give us this like little squiggly sign, that's an estimate of the overall atomic mass. So this is like the overall weighted atomic mass that appears on the periodic table. It should be about 1. If I'm just estimating, and it's 99.9% of all the isotopes are mass 1, then if I look on the periodic table, the weighted average better be close to 1. And so if I go back and look at my periodic table, oh yeah, up in the corner, then it's like 1.008. That totally makes sense now, right? Yeah, when you look at the periodic table and you see that a lot of the masses are really close to a whole number, it's just showing us what isotope is by far the most abundant, which also then means it's the most stable. So if I look at helium, similar, that 99.9999% of all the helium on the face of this earth is helium with a mass of 4. Atomic number is 2, so there's 2 protons. To get a mass of 4, there must be 2 neutrons. There is another naturally occurring isotope, helium-3, that has 2 protons and 1 neutron. But its percent abundance is crazy tiny. So just using my noggin, I would estimate that the weighted mass should be like 4. 99.99999% of all the atoms have a mass of 4. And so yeah, if we checked on the periodic table, helium, oh yeah, it's like 4.003. It just means that by far helium mass 4 is the most abundant. Same thing with nitrogen. There's nitrogen mass 14 and nitrogen mass 15. But 99.6% of all atoms are mass 14. So I would expect that the weighted mass should be darn close to 14, right? If I check on the periodic table, nitrogen is element number 7. Oh yeah. If I look at the mass up there, it's super tiny, 14.007. So yeah, that makes sense. So if we apply that same logic to carbon, 98.89% of all the carbon on the face of this earth is carbon-12. And there's very small fractions of carbon-13 and carbon-14. Carbon-14 is that radioactive, unstable form of carbon that can be used to help date, old bones and things like that. Okay, so if 99% of all the carbon in Earth, on the face of this Earth, is mass 12, then wouldn't you expect that the weighted average would be pretty close to 12? So let's check. It's my estimation. Carbon. Oh gosh, I've like almost written on top of it. So carbon is like right in here. And if I look up in the corner, it's like 12.011. Yeah, that makes sense. That the mass is really close to 12. Yeah, it's because it's by far the most abundant. But now, here's kind of what happens with bromine, where bromine has 2 naturally occurring isotopes, bromine mass 79 and bromine mass 81. All right, cool. Well, now if I look at the abundance in nature, they're almost equally abundant, whereas all the other ones, like one was by far like 99.9%. And now it's like about 51-49. Okay, so approximately 51% of the isotopes are mass about 79. Like let's say I just kind of average this, it gets approximately 79. And this is approximately 81. And that's what they're like showing us up here, 79 and 81. Okay, so let's see, what would we do here? This is like really close to 50. I mean, it's a little bit more than 50%, but like 51-49. If I just had to estimate, I'm going to say that this is going to be really close to maybe being like right in the middle of these 2 masses. It's approximately 50-50. I mean, I might guess, like just a whole number estimate, like 80. And if I had to make it like a little bit more specific, it might be like a little bit less. The smaller isotope is the more abundant isotope. Mass 79 is a little bit more abundant. So maybe it's like 79.9 or something. Let's go check the periodic table. I bet you're dying to know, right? Okay, periodic table, bromine. It was so close. Okay, look at this, bromine. It really does say like 79.904. Now for an estimate, I wouldn't estimate 0.904. That'd be crazy. But I could estimate that it's going to be really close to 80. They're about equally abundant. And if anything, the more abundant isotope is just a smidge less massive. Okay, now check this out. If you wanted to calculate the exact mass, then here's how I set it up. I'm going to use these percentages as decimals. So I'm going to say it's like 0.5069, and I'm going to multiply by the mass. So they're giving me the mass as 78.92 AMUs. Okay, so I'm going to plug that in my calculator because I can't do that in my head. 0.5069 times 78.92. Boop. Oh, whoopsies, I forgot. 0.5069. I was like, that number doesn't make sense. Times 79.92. There we go. Okay, so this gives me about 40 point, like 00-ish. And then I do the same thing with the other isotope. So the abundance, I'm going to say 0.4931, 49.31% of the isotopes have a mass of 80.92 AMUs. So we're going to plug that in our calculator. 0.4931 times 80.92. Okay, so that gives me about 39.90-ish. And then all we do is add. So I'm going to add this guy and this guy. Oh, what do you know? 79.9 AMUs. That's exactly what I found on the periodic table. Now, you could round and leave more decimal spots and get more exact, but I felt like 2 decimal spots might be good enough. That's how I would calculate the exact mass, if asked. But it's interesting just to be able to estimate a reasonable weighted average mass as well. All right, so then finally, my last little question in this section. Question 19. Compare and contrast. How does an element's atomic mass differ from its mass number? Okay, so when we refer to the atomic mass, it's calculated as the weighted average mass. Atomic mass is what we look at on the periodic table. We use these numbers all the time. But they're calculated, they're weighted averages that take into consideration multiple isotopes. Consider, we'll say all isotopes, their masses and their abundance. Mass number is just specific to one particular isotope. Refers to the number of protons and neutrons in one particular isotope. So for example, there's 2 different ways of showing these isotope symbols. I could have something like carbon dash 12. Or I could have carbon dash 13. Or you could see it with the symbol like carbon and then 12 and its atomic number is 6. Or carbon 13, 6. Well, that 12 or 13, that's the mass number. That's the mass number in reference to one particular isotope. It's the combination of the protons and the neutrons in that particular nucleus. But the overall atomic mass is calculated, averaging the different isotopes that exist and their abundance in nature.